Today we are going to build a Protactinium 234M generator. From a didactic perspective, it's one of my favorite experiments. So what do we have planned for this video? First, a rough overview to stay on track. We are going to build a generator using lab chemicals with a modification to a classic version and then proceed to do the experiment and analyze the outcome. After that, we will discuss the scientific and the didactic background. So uranium-238 decays into thorium-234, which then decays into Protactinium-234M, which then further decays via beta-minus decay into uranium-234. Protactinium-234M has a half-life of just 1.159 minutes. In the hydrochloric acid solution, it is, of all the radionuclides present, the one with the highest specific activity. The protactinium can be spatially separated from the other nuclides using a suitable extraction agent. Since the organic phase has a lower density, the protactinium is brought closer to the detector, allowing us to better measure the decay of protactinium. Due to the short half-life in the experiment, we can really measure the decreasing protactinium activity in the organic phase and then calculate back from that what the half-life of Protactinium-234M is. For the chemicals we need the solvent N-hexane, the extraction agent MIBK, the aqueous phase, 20% hydrochloric acid, and uranyl nitrate hexahydrate. Let's see if we can replace the N-hexane with normal washing spirit and MIBK with benzaldehyde. My spoiler for part 2. 2 samples with each 1 gram of uranyl nitrate will be weighed. The container has a capacity of 20 milliliters. Now the uranyl nitrate is dissolved in 14 milliliters of 20% hydrochloric acid. You could go with a 50-50 by volume mixture, but a minimum amount is needed for proper phase separation. However, don't use too much or you won't get high count rates. Into one container, 6 milliliters of MIBK is added and into the other one, 6 milliliters of benzaldehyde. The whole thing is then topped off with either N-hexane or washing spirit. Be careful not to overdo it, as there is a risk of contamination from the radioactive solution. And especially for the benzaldehyde, the whole room will smell like almond extract, which in this quantity can be really annoying. After letting it sit for a while, I find you can more clearly see the phase boundary with the benzaldehyde rather than with the MIBK and N-hexane. So onto the experiment. A Geiger-Müller counter is placed on the generator, preferably directly on contact. Even half a centimeter gap can result in unusable data. The generator should stand unshaken for at least 10 minutes before the initial background measurement can be done. In this case, the background was 8 pulses per 20 seconds. Essentially, you just proceed like a normal half-life determination. It's shaken for at least 10 seconds, and now as quickly as possible, place the detector on top and the measurement starts. Measure for 20 seconds and then pause for another 10 seconds. Measure for 20 seconds again, pause for 10 seconds, repeat for at least 6 minutes, so 12 measurement cycles. After 10 minutes you can definitely stop. Now onto Excel. It's a great introduction to the program and learn how to use Excel for scientific purposes. Here are some sample data. Based on the video, I checked that it took me 2 seconds from shaking to the start of the measurement. First one was with the benzaldehyde, another run with the benzaldehyde after a few minutes of pause, and then a run with MIBK. You can clearly see that MIBK results in much better extraction of the protactinium. But that is not what really interests us. What matters to us the most is the trend of the values. Of course, background corrected and then logged. It will just result in a better trend line. Plotted graphically with a trend line and equation, we can get the following decay constant, which we can then use to determine the half-life. This looks pretty good. As a comparison, here's the literature value. Now, fortunately, we had a master student who had done this experiment several times, and now we can just focus on the variant with the benzaldehyde. Raw data, background corrected, logged, and then graphically represented. And what's the difference between 5.1 and 5.2 that makes these values so bad? Well, I added some more hydrochloric acid to minimize the air bubble and overdid it. So be sure not to completely overdo it. The solution leaked, gloves were contaminated despite the paraffin sealing, everything smelled like almond extract, and the data became useless. So learn from my mistakes. But otherwise, you can definitely determine the half-life of protactinium with cheap benzaldehyde. Important, here we were working with chemically processed uranium, meaning that all the protogies of the uranium-radium series have been separated due to different chemistry. Only uranium remains, and it's still radioactive. Uranium-238 decays into thorium-234. this will eventually reach radioactive equilibrium. When is that? We say after 10 times the half-life of the daughter nucleus. Why? We only notice thorium is in there when it actually decays again, hence the half-life of the daughter nucleus. Realistically, you can easily measure it after 3 half-lives as well, but 10 half-lives is just a good rule of thumb. Looking at the chart of nuclei, yes, the uranyl nitrate has definitely been sitting around for long enough for the two to be in radioactive equilibrium. Equilibrium in this case describes the formation of the daughter nucleus from uranium and its decay into protactinium. Since the half-life of uranium is much longer than the half-life of thorium, we can call this a secular equilibrium. In this case, the activity of uranium is considered constant. So it decays, but the amount stays the same. Yeah, that's the magic of rounding. For all practical purposes, we are never going to be able to measure anything else. So the thorium-234 decays further into protactinium-234M, and the equilibrium also has been established here. This is also described as a secular equilibrium, since the protactinium-234 is kept constant by the uranium. It would be transient if we had a system solely composed of thorium-234 and protactinium-234M. We have 1 gram of uranyl nitrate hexahydrate. The molar mass is 502 grams per mole. So roughly rounded, we have about 0.47 grams of pure uranium in it. That has an activity of about 6 kilobecquerels. You should remember that the specific activity is around 12 kilobecquerels per gram of uranium-238. And when calculating that in your head, the natural uranium activity is just basically uranium-238. Since everything is in radioactive equilibrium, we also have 6 kilobecquerels of thorium and another 6 kilobecquerels of protactinium-234M. A little advanced side note, why does thorium-234 decay into protactinium-234M and not into the ground state? Looking at the spin of the nuclides, you can see a decay from spin 0 to spin 0 to 0 again for uranium-234. Quantum mechanically, that's allowed and therefore preferred. Protactinium-234G has a spin of 4+. A beta decay from 0 to 4+ is 4 times forbidden. Practically, it doesn't get any worse. Even an isomeric transition from protactinium-234M into the ground state would be too spin forbidden, so a beta decay directly from the metastable state is preferred. By the way, in this experiment we are measuring the 2.3 mega electron volt beta particles of protactinium-234M. That's a big nuclear background. Now onto the chemical background. Why HCl, why MIBK, why benzaldehyde? It absolutely needs an acidic medium to prevent the protactinium from hydrolyzing. Hydrolysis here refers to the formation of water-insoluble hydroxocomplexes, which could eventually precipitate as protactinium oxide hydrate or something similar. I don't want to delve further into the very interesting protactinium chemistry since it's not really relevant. The important thing is acidic medium at the concentration of 6 kilobecquerels per 14 milliliters. We are talking about tracer concentrations, and certain reactions such as the formation of condensate products aren't possible. Protactinium-234M is somehow soluble in acidic solution at these concentrations. I'm not writing protactinium 5+ because it exists as a naked 5+ ion, which it absolutely doesn't in hydrochloric acid, but rather in perchloric acid. But I just wanted to indicate that it's in the oxidation state of +5. Now looking at the MIBK, we can see it's a ketone. Structurally, it has a polar keto group and is mildly water soluble. Very likely the protactinium is complexed by the MIBK with the oxygen atom coordinating to the protactinium. The N-hexane phase was then to speed up the phase separation. We know this from the TBP in the Purex process. I'll put a link to that in the video description. There are other suitable extraction agents like DIBK, diisobutyl ketone, which was used in the extraction of protactinium-231. Video is linked here. Unfortunately, I made a mistake in that video. I said diIBK and showed MIBK. Both work, we just don't have the diIBK. What about using another suitable compound that isn't water soluble and has a carbonyl group? And what we had laying around was benzaldehyde. How awesome would it be to show a variant of this generator that could be built by easily accessible chemicals? So I used benzaldehyde in the first attempt and it didn't work as well, but it still worked. Maybe the benzaldehyde doesn't complex the protactinium as well as the MIBK, But then I read that in the United States, for example, benzaldehyde, unlike in Germany, is very hard to come by, so maybe vanillin could be used next? I think that would smell even worse, but maybe for another video. Finally, the didactic use. How awesome is this? We can measure something that's invisible with cheap household chemicals in Germany, learn to use Excel, learn about beta radiation, and learn to understand the mathematical description of a decay. And even better, when it comes to radiation protection, this generator doesn't need any shielding because it's pretty much a alpha-beta only emitter with very little gamma activity. You just need to handle the uranyl nitrate hexahydrate carefully and then it works. But can you do this in school? It would be fantastic to reintroduce such a visually engaging experiment when it comes to radioactivity. I mean, the experiment itself isn't new and the necessary components are even commercially available. And in the context of our state curriculum, it fits perfectly within the content field of atomic, nuclear and elementary physics, which is taught in the 10th grade. So there's definitely space for such an experiment in the physics lessons. Now on to the big question. Am I allowed to do this? Since we are working with a material that's radioactive, it falls under the activities regulated by Section 3 of the Radiation Protection Ordinance. As a physics teacher, you are allowed to conduct these experiments at the front of the class, but not as a student experiment, and I'll explain why in a moment. The way we've built this generator in the video does not mean the DIN ISO 2919 standards to be classified as a sealed source. So at the moment it lacks official certification. However, with an activity of 6 kilobecquerel, it's below the exemption limit of 10 kilobecquerels. Therefore, handling it in school is generally allowed without requiring special approval. From a didactic perspective, it makes little sense to use this as a student experiment, especially if you have just one generator for the entire class of 30 students. If you add a second generator, it would exceed the exemption limit due to the summation rule, pushing it into the category of regulated handlings of radioactive materials, and this would require then a radiation protection officer with the expertise S7.1, which is just an unnecessary burden. You can lower the uranium concentration to 1.6 kilobecquerels per generator and then have 6 of these generators in school. This could work if we get this generator to be approved as a closed source. If any physics high school teachers are now watching up to this point, feel free to email me and I can certainly give you more information about this experiment. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye!